Hello, welcome back. So we're now looking at the next chapter, chapter 8. Chapter 8 is called Rates and Equilibrium. We are going to do it in two separate sections almost. So we're going to concentrate first of all on the rates part of this section. So we'll be looking at the rates of reaction over the next few lessons. Right, let's get started. So, the first lesson is an introduction to the topic of rates of reactions. When I say rates, I mean the speed of a reaction. I'm going to explain how reactions happen. So some fundamental principles about how reactions happen. Right? Now, let's say we have two particles. Okay. Now, what's going to have to happen to those particles before they can react? What's going to have to happen to them? Well, they are going to have to collide. They're going to have to bump into each other. Okay. But particles are bumping into each other all the time. Most of the time, those collisions don't result in a reaction. So bumping into each other, colliding, is not enough. For a reaction to happen, the particles not only have to collide with each other, but they have to have enough energy when they collide with each other. So reactions occur when particles collide with enough energy. Reactions occur when particles collide with enough energy. There's a better diagram here, one I heard earlier. And it says there, collision theory. You often hear that expression about describe your answer using the collision theory. So everything we talk about in the next few lessons will be related to collisions and collision theory. But simply, particles have to collide with enough energy if they are going to react. Now that's a very vague term, enough energy. What do we call the amount of energy needed by a particle for it to react? Can you recall? Hopefully you remember us looking at something called the activation energy. The activation energy is the minimum energy needed for a particle to react. Or in a better explanation, a better definition, the activation energy is the minimum energy needed to start a reaction. And hopefully you'll recall this graph from the previous topic. If we have our reactants, okay, we have to give them the activation energy. That's the minimum energy needed to start the reaction. If they then get that activation energy, they can then react and release energy and form the products. Now in this example of an energy level diagram, the products have got less energy than the reactants. So this is an energy level diagram of what type of reaction? This is an exothermic reaction. But whether it be exothermic or endothermic, the particles, the reactants need the activation energy, which is the minimum energy needed to start a reaction. Okay? Now, some reactions, we can say, are slow. Some reactions are slow. They happen we wouldn't measure them necessarily in seconds. They might take minutes, hours, weeks for them to go to completion. Some reactions are very slow. A good example would be rusting. Rusting is a slow reaction between iron, oxygen and water. Some are faster. Most of the reactions you'll have seen in science lessons are quite fast reactions. A good one would be adding sodium to water. If we had a piece of sodium, Na, added it to water, you'll have seen your teacher do this. Do you know what two things it would make, a metal plus a water? Hopefully you recall it would make sodium hydroxide, NaOH. And what else would we see? We would see bubbles. We would see bubbles of hydrogen. We can balance that. So adding sodium to water is a fast reaction. As soon as the sodium hits the water, it starts to fizz, it starts to make hydrogen gas. It will be a very fast reaction and it will be over in a few seconds. Almost too fast for us to measure how fast that reaction will be in a science lab. Whether a reaction is slow or fast though, they all follow a similar pattern. All reactions tend to start fast. Okay? Then they slow down. And eventually, reactions will stop. Now, if you think about particles and collisions, why do you think all reactions start fast? Why are they fastest at the start? What will there be more of at the start? There won't be more energy. But what will we have more of? At the start, there are more particles to collide. At the start of the reaction, there are more particles to collide, and if there's more particles to collide, there'll be more successful collisions, and the reaction will be faster. Why do you think it would then start to slow down? What's happening to those particles? What's happening to the reactant particles? Well, the reactant particles are being used up. So, as the particles are getting used up, there's going to be fewer successful collisions. So the reaction is going to slow down. Eventually, why will the reaction stop? Eventually, there will be no reactant particles left. Once there's no particles left, the reaction is finished. Now, what we'll do in this topic, if we were in school, we would do many experiments where we try and measure the rate of a reaction. So in a reaction, we start with the reactants, and then they're going to get used up and we're going to make the products. What we could try and do, we could measure how much reactant was used up per unit time, per second or per 10 seconds or per minute. We would measure how much a reactant was used up. That can be quite difficult. So if it's difficult to measure how fast the reactant was used up, we can try to measure how fast a product was made. So we can either measure how much reactant was used up or how much product was made per unit time. That's how we would try and measure the rate of reaction, to know how much product was made per unit time. If you think about a reaction of magnesium with acid, okay? When we add the magnesium to the acid, it's going to start to bubble because a gas is being made. Now, a very simple experiment to measure the rate of reaction will be to count the bubbles, but we're not going to be doing that. If we add magnesium to acid, it's going to make a gas. But if we want to measure the rate of the reaction, we want to be able to collect the gas, and we'd use something called a gas syringe. We'd use a gas syringe and a timer, and once we added the magnesium, we would start the timer, and then every 10 seconds we would see how much gas was given off. Eventually, there will be no more gas given off as the reaction had finished. Why would this reaction be fastest at the start? Because there will be more magnesium and acid particles at the start. It will then start to slow down because the magnesium and acid particles are getting used up. But this will be a method used to measure the rate of a reaction if a gas was made. Now, in a similar reaction that's making a gas, in this example, we haven't got a gas syringe, but we've got a mass balance. We've had the reactants to the acid. A gas is going to be given off. The cotton wool won't trap the gas. It's just to stop any acid escaping. So in this example, we'd add the magnesium to the acid. A gas would be given off. What would happen to the mass of the conical flask and the reactants as the reaction proceeded? What would happen to the mass? It would start to go down. So we could measure the mass every 10 seconds and to see how much the mass was going down. Eventually, why would the mass stay the same? Because no more gas was being given off, so the reaction is complete. Another very famous experiment is where we have an experiment that changes colour, that goes from colourless to a certain colour, a colour that's opaque. And we can do an experiment where we can time how long it takes for an X that's underneath the conical flask to disappear. This is lots of examples of this experiment you can see on YouTube. But this is an experiment where the colour has changed, so we can time how long it takes for the colour to change. So, to calculate the rate of reaction, you can either measure the volume of gas given off per second or per minute or per unit time. We would use a gas syringe for that, providing the reaction gave off a gas. We could measure the change in mass per second or per minute. Again, that would work if a gas was being given off. Or we could measure the time for a reaction to change colour or go cloudy. Now that was just a brief introduction to the topic of particles and collisions. Just to recap, this is the first lesson on the rate of a reaction, on the rates of reaction. We're looking at particles colliding. If a reaction is to happen, the particles must collide with enough energy. And the minimum energy needed to start a reaction is the activation energy. We'll do a lot more in the next few lessons on what factors are going to affect the rate of a reaction, or what factors are going to affect the rate that the particles collide and the energy that the particles collide with. Hope that makes sense. Any questions? Ask your own teacher, and I shall speak to you later.